Alrighty, so we talked for the 10 minutes we spent on this with the crazy day on Thursday when I had so many interruptions first period, and then your class we had something. A polynomial could look something like this, like a negative 2x to the 5th. You already have a lot of this written down. 3x to the 4th, 2x third minus 5x squared plus 2x minus 6. That is your polynomial. And last week we talked about the degree of the polynomial. Can anybody look at that and tell me what degree it would be? Anybody look at that? What do you think, Kylie? Degree of 5. Absolutely. Alrighty. Today we're going to look at that and talk about what that degree and whether it's even or odd tells us about our graph. And then we're also going to look at this guy out front. He's going to tell us a lot about our graph as well. So, let me mark absent. We said that each piece of this polynomial is a monomial. A monomial is an expression without pluses or minuses. And each monomial is also called a term. So this polynomial has 1, 2, 3, 4, 5, 6 terms. And when we write it in descending degree from the highest power all the way on down, it's said to be in standard form. I said standard form. Now, the guy up front is our leading coefficient. He is very important for the rest of this lesson. He is the constant number that's in front of the highest degreed term. Okay? And the highest degreed term is called the leading term. And the very guy at the end, we already said, but some of us didn't get this, is the constant. He has no letters and no numbers. He is the number without the variable. Okay? So, today, not just looking at the degree, we're going to examine whether the highest degree is an even or odd number. That's going to tell us about our graph. And then the sign of the guy out front, the leading coefficient, is going to tell us about our graph. So, if we look at the next piece of this, we're going to use our leading coefficient and the degree of the polynomial, whether it is even or odd.
Connor's here.
Oh, hi, Connor. I think we got it on Thursday. And this is going to tell us how our functions are going to rise or fall without bounds. We're going to discuss what y is doing as x moves toward infinity or negative infinity. And we're going to know all of that by looking at the leading coefficient and the degree of the polynomial. Okay? All right. Connor, did you have a pass?
I was with Mrs. Amosmeyer. She said she'd send out an email.
Okay, that's fine.
Just for that accounting guy.
Yep. And our warm-up today, you don't have to do it on the half sheet, but in case you want the problems to review, was just the first problem. But do it on here. Thank you. All right. So, before we get to the next page, do you agree that, not that, we learned what the graph of an x squared term would look like? What's the graph of an x squared term? It's a parabola, okay? Now, is 2 an even or an odd number? Even. So pay attention. Any parabola type polynomial, his highest degree is going to be even. So when we have an even highest degree, it's going to resemble a parabola. It's not going to be identical, but you'll see that it's parent shape. Okay? If it was odd, do you agree that this was the parent function of an odd degree? All right? What kind of graph was that? You said it looked like a what? Yeah, like your S or your snake. So any odd, whether it's 3, 5, 7, or 9, is going to be very similar, not identical, to that guy. We learned at the beginning, one more review here. As x approached negative infinity, what did y do in this one? As x approached negative infinity, we learned this, what was y doing? Positive infinity, okay. On this side, as x approached positive infinity, what was y doing? Again, positive infinity. You guys were doing limits in calculus with that, you just didn't know, okay? So let's look at the next slide. According to what we just talked about, would this guy be an even or odd leading our highest degree? Because it's an S-type. Does it be even or odd? Odd, okay. And that's exactly right. We are having an odd degree. If your leading coefficient is positive, you're going to have to memorize, this is the basic graph. If your leading coefficient is positive, you're going to have the max coming from left to right and then the min. In terms of limits, when you get to calculus next year, all that says is what we talked about. The limit of y, remember f of x is y, as x approaches negative infinity is what? What is y approaching? You guys understand limits. You were doing it all along. The limit as x approaches positive infinity is asking, well, what's y doing? Positive infinity. That's it. That is the basis of calculus. When you took the difference quotient we did back in chapter 1 and learned that limits are what we are approaching, the y values to what x is approaching, you got it. So if this coefficient was positive, and now in this graph, it's still going to be an odd degree, what do you think the coefficient had to be to flip it? Negative. You got it. And as x is approaching negative infinity, what's y approaching? Positive. And the same thing, as x is approaching positive infinity, y is approaching negative. That's it. This is why I was so adamant about you learning how to interpret this back in chapter 1. And we're not going to do much with this, but this section does go to that. So, do you agree that this kind of relates to our parabola, our x squareds? You can tell the difference when your highest degree is even or odd. Both of these degrees are even because they resemble a parabola. This is when the coefficient is positive. All right. As x approaches both negative and positive infinity, as their limits approach, what is y approaching on either of these? Every even degree, this is what it's going to be. What's going to change is how many loop-de-loops you have down in there. And you shouldn't be surprised that a negative coefficient out front flips it. Are you laughing because I wrote the negative sign? It's hard to talk and write. You ought to try it up here. So again, we still have an even degree, but our coefficient is negative. So what are both of those limits approaching? As x is approaching negative infinity, what are we doing with y? Negative infinity. Oh my gosh, you guys should just move over to Cotton's room right now.
I already go there every day.
Yes, you do. And your SAT prep is only one semester, right? Do you do only math, or is it math and English?
Math and English.
Oh, Lordy. Okay, so we're going to do a summary, and then you guys are going to chit-chat about it. The domain and range for each degree. As x approaches both negative and positive infinity, on even powers, you should, as soon as you see the word even power, not Austin power, you should be thinking of your U-shaped graph. what do you know about the end behavior or the y values on even powers? Are they going in the same directions or opposite directions? Same. Okay. The end behavior is the same direction. Awesome. And on odd powers, what happens to our end behavior? Is it the same or the opposite directions? Opposite, yep. So all your hard work is probably making this a little easier. What do you think the leading coefficient, the A value, does as x goes to negative and positive infinity? If we have a negative coefficient, what's it do to the graph? It flips it, right? So doesn't it change the end behavior? It changes the direction of the end behavior. Alrighty, so what you're going to do with your groups is look at A and B. But we are going to hold off for right now on the turning points. I'll discuss those with you. But you should use your calculator, sketch the graph, and determine the end behavior. I'm going to give you about 2 minutes. Should resemble something, wow. Whoa, I feel like I'm getting car sick. It should resemble something like that. Okay. What did it look like? Did it look like that? Yeah, I think it was a little lopsided. So what did we do? We came down a little, went through, and then we came down a lot. All right. You should not have been surprised by the end behavior because it was an even with a positive coefficient. But moving right along, as x goes to negative infinity, what's y doing?
Positive infinity.
Yep, on both of them. And the turning points, as we go, we have 1, 2, 3. 3 mins and maxes, right? It's going to be 3 turning points. But the formal definition, as we go from decreasing to increasing, that's 1 turning point. Increasing to decreasing, that's the second. And then decreasing to increasing, that's the third. 3 turning points. I just go by maxes and mins. But can anybody see a relation between the power and the number of turning points? Look at that. What is it?
Subtract 1 and then
Subtract 1. That's it. Because, think of it. When you have a polynomial and you're trying to find the zeros, okay? The degree tells you how many zeros there are. The degree minus 1 tells you the turning points. So without even doing much to graph, by factoring your polynomial and then knowing about how many zeros you're looking for and turning points, you really need nothing to graph it. All right, so the formal definition here. Your graph has at most n minus 1 turning points, where the graph changes from increasing to decreasing, or vice versa. And the function has at most n real zeros. So that n is represented by the highest degree. So if I have a polynomial of x to the 5th, that means we're going to have 5 zeros or 5 solutions, and it's going to turn 4 times. Okay, so this is laying the foundation. The rest of the lessons will be nice algebra stuff. Alrighty, you should remember this from Algebra 2. When this slide flipped first period, I got a lot of, oh, I hated this. Anybody remember multiplicity? No? It's going to be easier the second time if you're one of the ones that hate it. we'll do the definitions, but when you actually see it, it'll be easier. If a polynomial function has a factor that is repeated, so we factor it, and you get the same binomial multiple times, these roots are labeled as the multiplicity. That's a hard word to say and spell, of the number of roots you're looking for. If you get a factor of c and it occurred an odd number of times, your graph is going to cross and actually pass through the x-axis at that root. If you have an even multiplicity, then you are going to touch but not cross your graph at that point. And this is the last thing we're going to talk about today, and then we'll talk about what homework problems you can do. Okay? So you have the graph given on the next slide. Just by looking at the graph, do you agree there's 1, 2, 3 turns? Right?
Well, I mean, I know, is that first one? Is that?
The first one counts. So you would think that this is an n to, or x to the 4th polynomial, right? Because there's only 3 terms. But what the multiplicity shows us is when you cross the x-axis, that is one of your roots. But when you bounce off of it, that's 2 roots. So this is going to be a degree 5. 3 plus 2. It's going to be a degree 5. But what you need to know, and this is the last section of your homework, how many times does this tell me to write the binomial x plus 2? 3. They have factored it for you. They have been very nice and factored it for you. How many x minus 1s? Okay. So that's why we should expect 4 terms, but we don't because of the multiplicity. Do you agree 3 is an odd number? So that tells us when we find that root or that 0, it means it's going to cross through the axis. It doesn't mean that it's going to hit -2 3 times. All that odd number 3 tells us is it's going to go to -2 and cross through it. Okay? The fact that there were only 2 of these, that even number, tells us that the root x equals 1 is going to hit it and bounce off. Alrighty, so that's why you don't graph the root of 1 twice, but you're going to curve and hit it and bounce off. That's what multiplicity is. So the last part of your homework is saying, okay, what is the multiplicity? Is it going to cross the axis or not? But just by looking at the graph, we could tell that there were 5 roots because of the turns and then the bouncing. Does that ring a bell to anybody from last year? Vaguely? All right. So if you get your homework